Hey guys, how's everyone doing? Sorry I am late. I have had a bit of trying to start all this meeting up. Let's see if there's anyone in the. Is there a waiting room present? Don't know. Is everyone okay? Oh, there are 21 people in the waiting room. Let me just admit. Oh, give me a sec. Let's check what this lesson is on. Oh. We'll get started in a couple of seconds. Hey, is everyone okay? Cool. Let's get started. Today we're doing, I believe the lesson was on periodicity. Let me know if I'm correct. Yep, periodicity. Can everyone hear me okay? Yeah, cool. Got that. Perfect. It's gonna be in. I'll wait a couple of seconds just to start. And we've got a couple more people slowly joining the waiting room. Periodicity. So I think now it seems to be slowing down, so I think it's now perfect time to just get started. I'll keep an eye out on the chat as last week. Let me know if there's anything going on. Just gonna keep an eye on the chat. Okay, cool. So we're going to start the periodicity session with a little bit on classification. So this is how we can classify basically what the periodic table is, how we can basically organize elements within the periodic table, and how that is basically done. So just a recap of some key definitions. What is a period, what is a group, and what is a proton number? If someone in the chat could message that. Period, group, and proton number definitions. Yep, so a period is a horizontal row, groups are vertical, and the proton number is, yeah, it's so period determines the number of electron shells. The group determines how many electrons in that outer shell there are. And proton number, which I'm sure you, so period is the horizontal row in a periodic table. So elements in the same row are quite similar. They have the same number of shells and therefore have quite similar chemical properties. A group is a vertical column in the periodic table. Again, elements in the same group are very similar. They have the same number of outer electrons and therefore similar chemical properties. So remember, same number of periods usually have similar chemical properties. Also, same group, they can have, yeah, same group, similar chemical properties. To be fair, period, probably not. if you're in the same period, you probably won't have the similar chemical properties. You can have a really varying range of chemical properties across a period, whereas in a group, you do have similar chemical properties. The proton number determines the position of the element in the periodic table. So I'm hoping all of you guys have a periodic table in front of you. The proton number or atomic number is should be the top number in the periodic table for you guys. So it'll go basically 1 for hydrogen, 2 helium, 3 lithium, 4 beryllium. A quick recap of all these key calculations. So the mass number gives you the protons plus the neutrons. Can anyone tell me why we don't include electrons in the mass number? Yeah, it has virtually no mass, right? Its mass is about 1/2 or 20,000. It's very, very small. It virtually doesn't count for anything. Atomic number, therefore, is just the number of protons. Usually in an atom, remembering that the number of protons is equal to the number of electrons. Yeah, in an atom, whereas in an ion, that is variable and subject to change. The number of neutrons is equal to the mass number minus the atomic number then, because you're just taking away protons from an equation where protons are present. Remember, the blocks of the elements are to do with where the outer electron is located in which subshell. So you have the s orbital. These are where the outer electron is in an s orbital. D block elements or the transition metals all have their outer electron in the d orbital. A lot of the properties of the d block elements, which I'm sure you'll talk about, I don't know how many of you are in A2 versus how many are in AS. A lot of the properties of the d block elements are to do with their position on the periodic table, and to do with their fact that the d orbitals often have varying energy states, whether they have or they don't have electrons. And you'll talk a lot about that in your A2 transition metals topic, which I'm sure we'll get to in these revision sessions at some other point. P block elements, outer electrons in the p orbital. Now, remembering that, so basically, most of the p block elements will be non-metals. D block are going to be metals, and S block are also going to be metals. S block are going to be quite reactive metals. D block are going to be more stable, but they're going to have very characteristic properties, and P block are going to be very characteristic as well with their properties. And that's what periodicity is. So p orbital between p1. Yeah. Does anyone know the ladder technique for knowing which element has what electron configuration? Anyone heard of this? I'll quickly show you. So it kind of looks like a ladder, which is why it's called the ladder technique. Higher, as in higher, Scotland higher. It should be in the Scottish higher. Oh. Okay. So basically, what you do is you draw an arrow. So let's say the first electron, the first thing to fill up will be the 1s. Then the next thing to fill up is going to be 2s. Then after that, it will be 2p followed by 3s. Then 3p, followed by 4s. Then 3d, followed by 4p, followed by 5s, and then you keep going in that kind of configuration. Does that make sense? You draw diagonal arrows, so you get this ladder, and then you draw diagonal arrows to see what fills up first. All make sense so far? Do I do these lessons every year? I do 2 lessons a week. The last week was my first lesson. I haven't done any of them before then, but I don't know how long this is going to continue for. The p block elements are between S2P1 and S2P6. S2P6 3D1, S2P6 3D10. Remembering also a couple of basic things. Remembering the order of how many fill up is 2, then how many are in P? 6, followed by 10, and then an F orbital, which you don't really need to, you're probably never going to get to an F orbital, is going to have 14 in it. 14 outer electrons. Yeah, so it's basically periodically increasing by 4. What else do you kind of want to be aware of? How does anyone have any good revision methods to remember kind of the order of this, like the fact that it goes S, P, and then D in the order of filling electrons? Otherwise, I can show you mine, but it's quite nerdy. Yeah, in A levels, you do tend to only go up to 4 subshell. That's why I'm saying you probably won't ever need the F. Anyone got any revision techniques on how they remember that? No. Okay, the way I remember it is it's like Power Rangers, because remember it's Power Rangers SPD, and that's kind of the order of it. So it's S first, then P fills, then D fills. That's the way I remember it. But if there were any other kind of good revision tools for that. Okay. So we're going to take a look at now the physical properties of period 3. So first of all, we need to be familiar with where period 3 is in the periodic table. So period 3 is running from sodium, magnesium, and it runs all the way to argon, aluminium, silicon, phosphorus, sulfur, chlorine, and argon. Yep. We're going to learn the atomic radius trends, the melting point trends, and the ionization energy trends going across the group. So the first thing, atomic radius. Remember, the atomic radius across a period always decreases, right? Because as I'm sure that you remember, there are the same number of shells in every, across a period, we have the same number of electron shells, but our proton number increases, right? So what happens to a term called charge density? What happens to the charge density? Density being kind of how constricted something is, charge being negative charge. What happens to our charge density? Charge density, the positive charge density increases, the negative charge density also increases. Yeah, the reason is because your nucleus has become more positively charged, which means that it can pull these electrons towards the nucleus more, which means that the nucleus is contracted, everything around it is contracted inwards, so therefore the radius decreases. Does that make sense? Because of that stronger attraction. Now, a little bit of a, probably we'll touch on this in this lesson anyway, but a little bit of something kind of different. What happens if you're going down a group? Why does this trend not continue? Why do we not have an increase in atomic radius as you go down a group? Increasing number of electron shells. Perfect, yeah. So these increasing number of electron shells will outweigh this increase in charge density, right? Because they provide like another blocking layer almost. The charge can't go past this as well as it used to be able to. And so this increase in electron shells basically block that force from pulling it inward, the positive charge. Yep. So period 4 across a group. Now, so as you can see, the atomic radius across period 3 decreases. Again, yeah, no shielding effect because the electrons are just being added to the shell of the element's atom. Atomic radius is how far the furthest electron is away from the nucleus. So the way you think about it is, let's put that as the nucleus. Let's put that as electron shell 1. Let's put that as electron shell 2. So the atomic radius of this atom is basically that. Whereas let's have a nucleus, an atomic radius, atomic shell 1. As you can see, smaller atomic radius. Does that make sense? The melting point of the elements across a period will change because of their structure and how they're bonded. So this is going back to your bonding and structure. So sodium to aluminium, how are those bonded? Metallic bonding. Perfect, yeah. So metallic bonding, as I'm sure you're all aware, is the electrostatic forces of attraction between the positive nuclei and the sea of delocalized electrons that run between them. Now, as we go from sodium to aluminium, the strength of these positive nuclei increase. Remember, sodium is +1, magnesium is +2, aluminium +3. So the strength of this positive attraction is going up, which means that the strength of their attraction to the sea of delocalized delocalized electrons is also going up. Yeah. So what does that mean? Well, that means that the metallic bonds within the metals get stronger, which means, as I'm sure you're all aware now, that melting point as you're going up from sodium to aluminium increases. Does that make sense? Yeah. Yeah, perfect. Cool. Now silicon, how is that bonded? So starting with sodium and magnesium, they're just going to show you more delocalized electrons, more higher positive charge, which means that the greater energy. I would recommend writing this down in your notes, guys. I think this would be a really useful 3-mark answer that usually you'll be given. So if you put those as your 3 points as a marking scheme, I can't imagine any examiner not getting you the answers marked to that. So I'd either take like some kind of ability to just put that down in your notes. Yeah, I'll give you a second or two to do that. Cool. Okay, now, yeah, sodium +1, calcium +2. As I can see, everyone has put in. Sodium has silicon, they've all predicted with a high melting point. And this is because silicon has a huge giant covalent macromolecular structure consisting of many strong covalent bonds. These strong covalent bonds require a large amount of energy to break. Therefore, silicon is going to have a high melting point. Yep. I put that down in your notes. So what do you think happens to melting point from phosphorus to chlorine? Decreases, yeah. Why? Well, no, sorry, melting point, it kind of goes like this. So phosphorus, sulfur, and then chlorine. And it's literally to do with how they're structured. So they're quite simple molecular structures, but phosphorus is P4, sulfur is S8, and chlorine is Cl2, which means, now as you can see, based on the number of atoms per molecule, 4, 8, and then 2, sulfur is going to create, going to have the largest number of electrons. And remember, as we know from our knowledge of intermolecular forces, van der Waals forces increase in strength based on the number of electrons. So the more electrons you have, hence the more atoms you have generally, the stronger the van der Waals forces, and therefore the stronger, the more energy required to break, and therefore the higher melting point. But simple molecular structures generally have low melting points comparative to all the other atoms we've got so far. So remember, the stronger the induced dipole forces. I think probably better than both of those, it's better to call them induced dipole interactions, because that is the most technically correct term. London forces is an old term. Van der Waals forces is a newer term, but at the end of the day, I called them induced dipole interactions in all my exams, because that, first of all, it tells you exactly what they are. Recordings will be posted to YouTube. It tells you exactly what they are. They are induced dipole interactions. So they're inducible in the sense that they're not permanent. They're not always there. They can be only there sometimes. That's what I'm talking about now. And dipole meaning that it is two ends of the pole with opposite charges. The difference between a permanent and dipole to dipole and a temporary dipole to dipole is about how they're created. So a permanent dipole to dipole is created within two bonding atoms created by a difference in electronegativity. So I'm sure you know about your covalent bond. Let's say you have hydrogen and fluoride. Which one of these has a higher, hydrogen and fluorine, sorry, which one of these has a higher electronegativity? F, yeah, perfect. Fluorine and electronegativity, as we're all aware of, is defined as the ability of an atom to pull the pair of electrons within a covalent bond. If you imagine it like a tug of war, it's the ability to literally pull those electrons closer to one side. And fluorine is really good at that. It's a very electronegative element. So therefore, the electrons within this double bond are going to move closer to this side. So therefore, fluorine is going to become slightly electron dense, whereas hydrogen is going to become slightly electron deficient, or slightly negative and slightly positive. And that's really kind of important. Because it is literally, it is that creates this permanent dipole. Whereas with an inducible dipole, let's say both of these are carbon. So there's no difference in electronegativity. The problem they've got now is, I'm sure as you're aware, electrons are in orbitals, right? So as is in the name, what are they going to do? They're going to orbit, right? They're going to orbit. They're going to move around within the shells. So they're moving around within their shells. These electrons, so at any given moment, basically, more electrons could be on one side of the atom compared to the other, right? So more electrons, as you can see, these electrons are spinning around. More electrons could be on one side compared to the other. So more electrons could be on this side. So let's say we've got move these electrons. Sorry. Let's put these electrons here. So loads of electrons on this side, very few electrons on this side. Now, remember, because these are already oppositely charged, what's that going to do? Push the electrons on the other bonding atom to do? Move as far away as possible, right? Because electrons, like charges, repel. So these are also then going to do the same thing. Delta negative, delta positive, delta negative. So now, as you can see, oh wait, sorry. I meant if the electrons were on, I think this would only work if the electrons were on the other side. Give me a sec, sorry. It would only work if the majority of the electrons were on this side. So now that's delta positive, that's delta negative. And so as you can see, they push those electrons on this side, and now there's a strong attraction. There's a weak attraction between this delta negative side and the corresponding delta positive side on the other atom. And you can have more of these between more atoms. Does that make sense? Whoever asked the question, what the difference is? It involves the atom's electron. Yeah. So the induced dipole-dipole interaction does not really involve the electrons in the bond. It only involves the electrons in the atoms, in the atom, not in the bond. Yeah. Perfect. Okay. Remember, the larger the molecule, more electrons, more stronger induced dipole-dipole interactions, and therefore more energy required to break those stronger induced dipole-dipole interactions. Okay, and last but not least, so sulfur is the largest molecule, most electrons, strongest in van der Waals, so the melting points are greater. Argon has a really low melting point. It's a noble gas, exists by itself, so therefore it has very weak to basically none van der Waals forces. That's why it's called the noble gas. Okay, this is the last bit. This is probably the hardest part. What happens to ionization energy as we go across a period? Yeah, there is a general increase, but you will be, for most courses, you will be expected to be acutely aware. Oh, sorry. You will be expected to be aware of most of the increases and the decreases in ionization energy. So as you can see, there are dips, and you will be expected to know why the dips are there. So first of all, we're going to talk about the general increase. Remember, the general increase, proton number is increasing. We know that the radius is decreasing. There's a stronger charge between the nucleus and the outer electron. Therefore, surely by logic, it's going to be harder to lose the electron. Yeah. So it's going to need more energy, therefore, to remove that last electron. Yeah. So that's kind of logical. The things that the slide isn't going to tell you, but I will, is there are the dips. And these dips are at aluminium and at sulfur. So the aluminium one is quite logical. Sodium and magnesium are both filling in the s orbital, right? By the end of magnesium, you have got a fairly nice full s orbital. So magnesium is quite stable. So it's going to be quite hard to remove its electron. Now you've added another electron into a p orbital. That p orbital is unbound, it's unstable. It is not it's not going to be easy to remove. because it literally is by itself. It's going to be slightly easier to remove because it's unbound and it's by itself in that aluminium atom. So that one's quite logical. P orbital. Actually, I'm just going to type it because I'm sure my handwriting is probably not the best. P orbital alone, so easier to remove. Yeah. Now sulfur. Does anyone already know why sulfur there's a decrease? I just want to see how people are. It's to do with electron repulsion. Yeah. So it's to do with a rule that you probably will have come across at some point about how electrons pair within a shell. I cannot remember the name of the rule. So if anyone can and could put it in the chat, that would be amazing. It is electron pair repulsion, but I'm not exactly sure what the name of the rule is. So understand that these are going to be half arrows, but I'm doing them. So aluminium has the first electron in the p orbital. And remembering from this rule, we don't pair electrons don't like to be paired. Electrons hate because paired electrons repel each other. Electrons like to be alone. So we fill the second orbital within the p subshell. Then we fill the third one. But now we've filled out by phosphorus. We're on the increase. It's not Vesper. Vesper is to do with shapes of molecules, which we can talk about slightly later. So sulfur is on, phosphorus is on the up, but sulfur now needs to fill its electron somewhere. And so where does it do? It starts to pair up. And now this pairing of electrons within what is considered the, tell me if this is nomenclature you don't understand or naming structure you don't understand. The 3px orbital. I'm hoping you've heard of that. Yeah, please confirm that that's not something I'm just, my school just made up. Nope, never heard of that before. Okay, so basically the way when you're naming orbitals within a subshell, you name them X, Y, and Z. So if you're talking about a specific orbital within a specific subshell, you can refer to it as the 3px orbital or the 3py orbital. So this is the X orbital, and we're talking about electrons pairing up within the 3px orbital. Now, these electrons are paired up within that 3px orbital, which means that now they're going to repel each other. And this repulsion is going to lower the stability. So, as you can imagine, that's going to lower stability, which means that it's going to be harder for it's going to be easier to remove that electron because that electron is already doesn't want to be there. If you think about it, like it's easier to remove a student who doesn't want to be at school than to remove a student that does want to be at school. I mean, and this electron here does not want to be in this orbital because of the repulsion. So it is going to be really easy to remove that electron, or easier than it is to remove the unpaired electrons in the other orbitals. Does that make sense? Yeah, everyone okay? Oh, are there people in the waiting room? Yeah, cool. I'm getting a couple of yeses, which I'm taking that. If you have any questions so far, please let me know. Does this apply for chloride and argon? No. So between Cl and Ar, remember, they're all p orbitals anyway. So by the time from sulfur, you go back up. So after sulfur, you're going back to increasing from Cl and Ar. And Ar is actually quite stable because it's got a full p subshell. So it's really, it's very stable. Yeah. Cool. Unlike the last lesson, we can actually today have a go at some exam questions, which would be quite helpful. I'm going to go with AQA exam questions. As I mentioned in the biology session, it is very useful. I'm just picking AQA questions because most of the people who we polled tended to do AQA as their exam board. So we're going to pick AQA based questions mainly in the sessions. Okay, we're not going to do any of those. I'm gonna try and find like a long answer question that I'd like people to have a go. Oh, yeah. So not that one. Have a go at F and then FI and II, please. And then when you're done, type it in the chat. So I'm going to give you about beryllium. Why does it have a lower ionization energy? And why does helium have a higher ionization energy than hydrogen on lithium? Sorry, that question, I don't know the grammar. Beryllium, why does it have a lower ionization energy? A lower ionization energy than what? Than lithium. Why does beryllium have a lower ionization energy than lithium? Is that what you're asking? Not beryllium should have a lower first ionization energy than lithium, from what I know. But I can check. Yeah, no, sorry. Lithium does have a lower first ionization energy than beryllium. Sorry, I think that might just have been a mistake in your notes. And why does helium have a higher ionization energy than hydrogen? Well, that's to do with stability, because remember, hydrogen fills out 1s1, so it's the first electron in the 1s orbital. And helium is the second electron, so it's going to be more stable anyway. Okay, so we've got some answers here. So yeah, there's an increase because of the increasing atomic number and the strong electrostatic attraction between the nucleus and the outer electron. Yeah. Yeah. Perfect. I'm just going to say for both Sarahs, there are two Sarahs, I would expect you guys to probably say a little bit more to get the marks in your question. Same with Romana. I think probably looking at Shreya's and Brooklyn's answers, they're the right level of depth that we're looking for. So you'd probably be giving at least 2 points there. So something where you're saying you're probably going to get a mark in that question for writing increasing atomic number or increasing proton number. You might get a mark for strong electrostatic attraction and between the nucleus and the outer electrons. No, electronegativity is to do within a bond. So usually ionization energies are not related to bonding at all. So electronegativity does not really have to do anything with ionization energies. It is just about the increasing proton number. But yeah, as I was saying, yeah, you would probably be giving a little bit more detail. There. Okay, should we talk about why is the first ionization energy of sulfur lower than what would be predicted from the general trend? So this is back to what I talked about towards the end, which is slightly more confusing and a little bit hard to understand, but hopefully you guys manage to get the gist. Otherwise, we'll find out. Yeah, perfect. Specifically, you want to talk about sulfur where the electron repulsion is going on. Yeah, so it's the idea that the 3px electron now fills with an electron pair, and it's based on. Actually, I'm gonna find you guys the rule. By the way, I think that would be quite useful. Just the name of the rule. It's called Hund's rule. Yeah, it's called Hund's rule. It's about upspin and downspin. Yeah, I don't know if you guys will have heard that term in school, but yeah, that was the one I was talking about. Cool. Okay. Phosphorus to chlorine atomic radius trend. Increase. Yeah. Why? Yes, the atomic radius does decrease. It decreases because of the, as you know, the increasing atomic. Increasing proton number, which means that charge. Greater pull on the electrons. Perfect. Yeah, that's exactly the kind of stuff we're talking about. What was 3A? Why these elements are, because their outer electron is in the p orbital. That's it. That's the answer to 3A. Yeah. Right. Let's open the floor to any general questions you guys might have. We've got about 8 minutes left. Any general questions? It doesn't have to necessarily be about chemistry. It can again be about anything, even medical stuff. If you're looking to do that, doesn't matter. Just any general questions? Next lesson. Are you talking about chemistry or biology? Generally. Usually the biology lessons tend to stick around a little bit longer because there's more content to cover in the same amount of time. But yeah, are you looking at chem or bio? Both. I can double check for you. It's good. I do bio ones as well, yeah. The first bio one is on YouTube. So if you just go on the Study Mind YouTube, you'll find the first bio lesson. For the reduction of nitrobenzene. Yeah, the chemistry one will be put on YouTube like the biology recording. Should be anyway. The next biology one is about immunity and disease, which is a really interesting topic. So I do recommend coming for that. Then the next one, also for chemistry, is going to be about energetics and equilibria. Sorry, let's answer for the reduction of nitrobenzene. Why do you need sodium hydroxide? I'll show you. Because you need to form a hydride ion. And there's a really cool mechanism for it. You don't really need to know the mechanism, but it is quite interesting to know. So basically, what happens is, so the OH minus, so sodium hydroxide basically releases this hydride ion. This hydride ion will then break the bond in nitrobenzene, the double bond between N double bond O, and create an OH group. There's an O minus left. That creates the diol. The diol then reacts with water to form N double bond O, which then again further reacts. And this is mainly done based on the OH minus will provide that hydride ion. Do we cover any? I was planning to cover A2 topics after Christmas because I didn't know where you guys would all be up to with your school stuff. Yeah, so you need sodium hydroxide because sodium hydroxide provides the hydride ion. Let me know if that makes sense, by the way. So what? Yeah, well, you could replace that with something else. So sodium hydroxide could be replaced with NaBH4, for example, which is another replacement. You could do it with that instead, but normally we do it with sodium hydroxide because it's much easier to work with. Wait, so this is no, this topic is A2. This is an A2 topic. Reduction of nitrobenzene. I think it comes up in the amines topic in module 6 for most people. What would I recommend for chemistry? So then 10. Yeah, I think usually the thing is, understanding the principle isn't necessary at A-level chemistry. You don't need to understand why we do something or why we do things in certain ways. And so therefore you don't need to know why sodium hydroxide is used. You kind of just need to memorize that it is used, which is why exam answers don't tend to include them. I actually did have a friend though who put sodium hydroxide, he put sodium NaBH4 as one of his answers to that question. He was credited with the mark, but even if they weren't included in the mark scheme. So you can put it down. You will probably be credited because your markers are proper chemists, but the best way to do it is just memorize that you do need acid and tin. How long does a full MMI last? MMIs last for, depending on the uni. So Exeter's is about 21 minutes with breaks. Bristol's is potentially 50 minutes. It depends on your university. What resources do I recommend for chemistry? Best ways to revise for chemistry. Exam technique is your key to chemistry. Understanding can be done through YouTube videos, lectures, watching videos. I recommend YouTubers like McChem Guy, very good YouTuber. He's got an amazing channel. ALevelChemistry as well for those AQA folk. Those are your big your YouTubers they're gonna be able to teach you the content, and then revision is done through exam technique, making those exam answers. You need to memorize definitions. Those definitions need to be ingrained. Biology webinars, there's a separate link, should be in the group chat. I don't know if anyone here has got the link to the group chat. ALevelChem has done most exams. Yeah, I didn't use ALevel at all for my chemistry because I did OCR, and OCR's master is McChem Guy. McChem Guy is truly incredible for OCR. He was the guy I used, but ALevel apparently has done most examples, so you can use them, and then exam technique. So that's done through all exam practice. Also, don't feel ashamed in doing other exam boards, exam questions. Most of my MacChem Guy. Although Chem Guide is also a great website to use, as well as they've got some good questions in there. MacChem Guy. Yeah. What was the other? There was another question in there. Yeah, A2 topics will be covered after Christmas. I'll send out a proper full timetable for it. Yeah, MacChem Guy. That should be on YouTube. He's the best kind of chemistry YouTuber I know anyway. Let me see if I can find his channel for you guys. This is kind of what he looks like. Oh, sorry, you can still see my screen. If you can find his channel is amazing. He's got a credible playlist. He's got even quick revision. Quick revision are like 7-minute videos on key concepts and topics. He's great. Do recommend him entirely. Link for biology. Again, it should be on the WhatsApp group if you're on that. Otherwise, unfortunately, I don't get the link. I get told when to turn up and where to go, and that's about it. So I don't get sent the link. If any other students are here who have lessons, who have the link to the WhatsApp group, please, if you can just share with them the biology link, that would be amazing. If you just put it in the chat. Do I do maths lessons? No, I was incompetent at maths. I didn't. I struggled with so much with A2 maths that I don't teach maths anymore. Also, I don't think I'd be very good at it. I think like now it's been 2 years. I've probably forgotten most of like my differentiation and integration skills. I can do GCSE maths and that's about it. Right. Anyone else have any questions? Do I have any recommendations for maths teachers? There are some great maths YouTubers out there. There are, like, whatever example you're doing, there are incredibly good maths YouTubers out there. There is TL Maths. There are some really good, yeah. TL Maths is really good. I recommend him. He's got loads of like introduction to proofs and stuff. I do recommend just using the maths lessons they've got. Or if you are looking to get like paid tutoring, Medic Mind has a lot of maths teachers as well, who are far better than me at doing maths related stuff. So they can also help you out. Also, what's that website? Hegarty Maths. I think they've got some A-level math stuff now as well. They're really good for work-throughs as well. Yeah. Again, if anyone has the link for the WhatsApp group, please can you send it on the chat? So this might help someone out. Is there a chemistry WhatsApp group as well? There should be just one WhatsApp group for both. I was fairly sure there should be one. I've not been added to either of them, which is kind of weird because, yeah, I could answer your questions on it, but yeah, I've not been added to either of those WhatsApp groups. Sorry, I literally have only given what I'm told. Right, I'm gonna have to run. I've got to go teach another interview lesson right now, so I'm gonna but I'm gonna leave the chat. No, actually, I'm gonna shut the meeting down. Hopefully I can see some of you at the biology lesson on Sunday. Otherwise, yeah. Otherwise, see you next week. Bye.